Alrighty, so section 1.3 is all about lines and planes. Okay, obviously some big deals about this. When you get a line, obviously, whether it's in 2 dimensions or 3 dimensions, and when you are there, obviously, there's at one x value, there's going to be one y value. At one x and y value, there's going to be one z value. However, that's not true on a plane, of course. Plane just keeps going on forever. Here I'm at a particular x and y value, but I won't necessarily. But here I'm at a particular x value and a particular y value with the z value out of. That's true. However, I can come over here along this x plane or along the x or along the y direction. Of course, my z's will change. And of course, it's three-dimensional deal, whereas this is just a point coming through space. That seems obvious. Now, when you do this, of course, plane, obviously with a line in 2 dimensions, of course, you're having I got a couple of points. I don't know, something easy, I guess. Oh, look, I got to find the slope. Sure you do. Okay, well, what is the slope? So the slope is a change in y over a change in x. All right, cool. So that would be 2 over 1, or just 2. But this is really, if you will, a dy dx, if you think about it. Okay? And so it's the change in y with respect to our only, in this case, independent variable. So, of course, you can write this equation something like this. Y equals, of course, 2x, or I'll write mx, I should say, mx, or maybe dy dx, plus some constant. Okay? That's one way to write it, of course. Another way to write that, of course, and you may remember this, is you had y minus y1 over x minus x1 is equal to dy dx, or the slope, if you will. So a person could write it this way. And that would totally be fine. And then a person could take it a step farther and go, hey, look, subtract over to the side, and you will get minus y1 equals a goose egg. Okay, and so that is one way that we will write, of course, the equation of a line. Now, this is known as so this is one way of doing it. I personally like this method the best. Now, when you go to do a plane, it's very similar, except instead of just having this and this and this, you're like, wait, this maybe if I did this minus this equals dz dx. Nice, but they're partial derivatives. Pardon me, I have allergies. Nice. Equals already equaled. And then, of course, you could subtract, and you get the exact same picture as before. Equals 0. Okay? And that is a very nice and very easy way to write it. Very straightforward, very nice. Now, when you do this is a plane, okay? But when you look at this guy here, you think to yourself, wait a minute now. Say, if I were to do this, I could factor this out. And then I can multiply it by, or not multiply it, dot product it with equals 0. Okay, and that's one way to do it. And so we're going to talk about several different versions of this guy as we go along. And you'll see what I mean by that. There's several different ways to approach this. This is my personal favorite, either written in this format for a plane or this format for a plane. Those are my 2 favorite ways. Now, your book shows a couple other ones which are important as well, and I will walk you through their normal form. In essence, this is the normal form. These are both normal forms. They have to take it to another level, and kind of I'll demonstrate that momentarily. Not a big deal, but I want to kind of show everyone how that kind of plays out. Now, if you think about this for a minute, suppose you have 3 points. Now, I do this because it's coming up soon, but the idea of a cross product comes up later. Yeah, we've not covered that yet, and it doesn't come up till later, and so it's a little annoying that they don't do it when I think it should be done. But whatever, no one asked me. I just work here. So if they had asked me, listen, I would have taught a cross product before I bring up the lines and planes. I think that makes my life easier. I think it makes it better. But if you think about this just for a moment, because this is how this is how I like to do it. The reason we have to have 3 points is because we need 2 vectors. We need 2 vectors, and with 3 points, there's actually 1, 2, 3, 4, 5, 6. There's actually 6 vectors that you can do. Okay, and so for instance, I could come from here to here. That would give me 4. Oops, these are points. Stupid, not vectors. But from here to here would be 4, 5, 7, and from here to here would be, for instance, 1, 4, 2. Okay? And so what we need, because all 3 of these points are in the plane that is my surface here, I need a vector that is normal to that plane. And so to do that, we're going to do what's called the cross product. Most of you have seen it before. If you have not seen it before, I will show you, A, how to do it the hard way, B, how to do it on my calculator, but most importantly, show you why it's important. A cross product is the determinant of this vector. Okay, remember where I is the unit vector in the x direction, j is the unit in the y, k is the unit in the z direction. So if I take the determinant of this guy, it's going to be I times, and then when you expand by minors, you get 4, 2, 5, and 7, minus j, always minus j, 1, 2, 4, 7, plus k, 1, 4, 4, 5. You get 28 minus 10 is 18i. And then you're going to get 7 minus 8 is negative 1, so plus j. 5 minus 16 is negative 11k. So what you've done here is you have found 18, 1, negative 11. In theory, when you dot that with 4, 5, and 7, you should get 0. It should also be true for 1, 4, and 2. So we'll double check that that's true. Okay? So that's going to be 72 plus 5 minus 77 is indeed a goose egg. That's cool. And 1, 4, 2, 18, 1, negative 11 is 18 plus 4 minus 22 is indeed a goose egg. So that's cool. The idea there being is we have found what we call the normal vector. So back to our thing here, dz dx, comma, dz dy, comma, negative 1. This is the normal vector. Okay, it's a normal vector. So in the way we had it set up previously, you see that? It's the way we had it previously set up when we were given those points. But in this case, what we're going to see is this. We just found ourselves a normal vector. This guy right here is the normal vector. So we're going to have 18 x minus something plus 1 y minus something minus 11 z minus something is equal to 0. Now let's look at that for a minute. What are we going to use for points? Well, any of these points that make me happy. So I'm going to use 327 just for a good time. Done. That is the equation of the line, or the plane rather. Now if you want to distribute it out, you're certainly welcome to. And if you want to subtract all your other junk to the other side, you're certainly welcome to, and get 18x plus y minus 11z 6 positive 21, I guess, equals 0, or you could subtract that over there and get negative 21. These are all the same way of looking at it. Now, on the calculator, what you can do is this. You can type in your vectors. So let's go back up and get our vectors here. If you want to use a cross product on this, you're certainly welcome to, although I will hold you responsible to be able to do one by yourself, by hand, I should say. Oops, so 4, 5, 7. Oops. So make sure that whenever you're doing, you learn how to do it both ways. I think that's important to understand what we're talking about. So vector ops, cross product. What you'll see, and we'll learn cross product rules a little bit more later on. If I do them backwards, I got those numbers there, which I got this time. Had I flipped them around, comma, that guy, I would have got the negatives of them. Okay, but my answer still would have come out the same. Down here, everything would have been opposite signs. And at which point, come on, move. There you go. Sorry about that, friends. All right. At which point, everything would have been negative of what they are currently. You could flip the signs, and you'd end up in the exact same location. Okay, so that kind of a big deal to me. I think cross products are pretty important, and quite honestly, no one asked me. But if they had have asked me, I would have started with that personally. Okay, now that normal vector is kind of a big deal. Okay, now the way your book does it, it's a little weird. I don't really like the way they do it very terribly much. So to me, well, I'll show you a couple ways to get there. Okay, so but personally, if you start with me and you ask me how I'm going to do it, that's how I'm going to do it. So I'm going to start off with these points again, the same ones from last time. Actually, I'm going to do this. One moment, please. I'm going to capture this picture and reuse it. But I'm going to attempt to do it the way, oh, no, that was terrible. I'm going to do it their way now, or one of their 2 ways they show in your book. So that when you do it, you can follow along and go, oh, I see what he's talking about now. Hopefully, anyway, that's the premise of the problem. Paste. No, it's disturbing. All right, shrink, Jay, shrink. Shrink the bit there. That's more better. Awesome. One moment, please. Now, another way to do this problem is to do what's called the vector form. Okay, this one, it's fine. There's nothing wrong with it. These two, instead of looking for this is how your book gets away without doing a cross product. Me personally, I always like the cross product. I just find it easier. Is instead of teaching with the cross product method at this juncture, they say, listen, let's take the two of the 6 possible vectors that you have in this plane there between these 3 points, and let's write an equation with them. And so it looks like this. So you have a vector x, y, z. That is, in other words, you have a lot of x, y's, and z points on this entire plane. Yes, there's a ton of them. There's infinitely many of them. And so how you're going to find them is you're going to start off with a p, an initial point, if you will. Okay, so this is p, was what your book refers to it as. Now you're like p. Is p going to be a vector then? Again, p is going to it has to be a vector. How do I know it has to be a vector? Okay, well, when you set that up, if it's not a vector, you have a vector equals a vector. Oh, if this is a point, that doesn't work, you see. Plus u times, well, I'm sorry, back that train up a little bit. I'm sorry, s times u, which is one of our 2 vectors that we currently have, plus, and then your book uses t for this other one here. I always have to look because it's kind of a weird deal. And then they call this one the v vector, yes. And that's our other vector. So all you have to do is come in here and go, oh, cool. So x, y, z is given by one of these points. Maybe I do 0, 1. Well, I'll do 327 again. I'm going to start at 327. And then I can go plus, and then s. You're like, what is s? All right, I'll show you in a second. Just relax. 1, 4, 2 plus t times the other vector, 4, 5, 7. Well, what does that get us? Oh, get you this, friend. Check it out. So if you start and you let s equal 1, t equal 1, for instance, then where will you end up? Well, you'll be at 3 plus 1 plus 4 is 8. And you'll be at 2, 4, at 6, it'll be 11, and 7 and 7 is 16, I think, yep. So in other words, this is a point on that plane. Well, if you recall a minute ago, we had just a different version of this guy, and it was somewhere, where was it? Right here. So 18x, oh, I like this one better. Let's do that guy, shall we? Oh, why did I circle it? That was stupid. I'm going to highlight it and copy it, man. Okay. So, come over here. Let's see if that's true. In other words, if this point's on the graph, what should happen? Well, it should equal 0 when we plug those values in. So, 8 minus 3 is 5 times 18, 90. Plus 11 minus 2 is 9, so 9. And then 16 minus 7 is 9. So minus 99. Hey, hot diggity dog. It works. Check. And so, again, what are you doing? You're just saying you're starting this about at this location, and from there, right here, you're going to go out this direction. You're going to follow the two vectors. So one of your vectors is this fella, and let's say I went out 1. Well, that put me here. And then I'm going to follow this vector, and it took me out here 1 unit. You see what I'm saying? Out here, and then out here 1, and that you're at some point out here. But I could just easily have gone, for instance, -1 in this direction, and then, I don't know, -1 in that direction, yes? Or I could have gone any number of them. And fractional versions of them cover every point on the plane. Okay? Now, it's probably the easiest one to do. It's just the most kind of annoying because you're like, oh, that's great. Hard to find exact values for this guy. For instance, let's say I want to have x equals... or I want to know what z is when x is this and y is this. Can I do it? Well, yeah, it's tricky though, right? So, for instance, down here, I solved this guy. Well, I didn't solve it. I had this a minute ago. Did I have equal 77? I think that's what I had, didn't I? I think so. I should probably check before I screw this thing up. Too bad. Equals -70. No, equals 21, you stupid idiot. Equals minus 21. There you go. Equals minus 21. There we go. Now, could a person solve for z pretty easily here? Well, yeah, I feel like you could. In other words, I tell you x and y. Bam, you can tell me z right now, yes? It's pretty straightforward, I think. And that seems easily to do. Crap. How are you going to do that up here? Very carefully is how you're going to do it, friend. Very carefully. But let's just say you do this. Let's say x equals 1, y equals 2. Could you, in theory, solve this equation and find out what z is? Yeah, but it would be hard. But yeah, how would you do that? Well, you'd say 2 is equal to 3 plus s plus 4t, right? And then you would have y is equal to 2, so 2 equals 2 plus 4s plus 5t. And you have to solve these equations, yes? And to do that, what would you end up with? Well, let's see here. Gross. There's no good way to do this. That's just, it's more algebra than I want to do this afternoon. S plus 4t. And then if I subtract this 3 over there, I get -1. That's hot. And I'm going to have 4s plus 5t. Sure. And the 2 minus 2 is a goose egg. That's hot. All right. So if I times the top one by 4, for instance, I get 4s plus 16t equals -4. You never know when you have to impress the ladies doing a little bit of algebra, you know, at the bar or something. Hey, ladies, watch me solve this equation here. Yeah, right. 4 minus 4 is 0. 5 minus 16 is -11t. 0 minus a minus 4 is 4. So I believe t is -4/11. That's nice. Gross. 4s minus 20 11ths equals 0 if I plug it into here, I believe. And so you get 20 11ths equals 4s, s equals 5 11ths, I believe. That's great. But what does that do for me, Jay? Well, then you plug it in. You get z is equal to 7 plus, you get 5 11ths times 2 is 10 11ths. And then you can have negative 4 11ths times 7 is negative 28 11ths. Which I need a calculator because it's just too late in the day to be doing algebra. 7 plus 10 11ths minus 28 11ths. Yeah, it's 59 11ths. Duh. Yeah, 59 11ths. Cool. By the way, down here, I could have just plugged in what values did I use for x and y for 1 and 2. I could have just plugged 1 and 2 in there. I'd had 18 plus 2 plus 21 over 11 is it's 20, it's 41 11 or 41 11ths. I just feel like that was an oops. Wait. Somebody messed up somewhere, J. One moment while I fix my boo-boo. Well, that's just embarrassing. I can't read my own handwriting. What an idiot. X is equal to 1, you clown. Oh, let's try it again. That's a little embarrassing. It only took me 10 minutes to do that off camera, by the way, just in case you're playing along at home. Idiot. I'm like double-checking everything. Did I get the cross product? Yeah. Did I do that? Yeah. All right, let's try it again, Jay. See if you can do it right this time. Idiot. All right, so I'm just too late. Yeah, look, I checked literally everything. But whatever. Anyway, I'm going to come up here and I'm going to solve this equation. I'm going to do it right this time. What are you doing? Clear. Try again, stupid. Idiot. There you go. Now come back to the front and make x equal to 1. How about that? No. Oh, hey, there you go, stupid. Atta bib. So x, so this is my x, that's my s. So s is 10 11ths. And my t is negative 8 11ths. Anyway, here what I was trying to do is plug these back into that equation. So you're going to get z equals 7 plus 2 times 10 11ths is 20 11ths. And then 7 times 8 11ths is minus 56 11ths. And so you're going to get 7. Hey, 41 11ths. What do you know? It better be the same. It's the same freaking plane, you clown. Yes! All right. Anyway, what I wanted to show you was it's so much easier to use this format. That's why I don't particularly care for the other format. It doesn't do anything for me. I don't really like it. You're like, well, can I get from one to the other? Nah, not really. No, not really. So just be aware of that. So I will have you doing both just so that you're comfortable with them and you feel good about them. But I don't want you to freak out about it at all. Okay? Now, they take it one step further and they actually take, and I'm just going to write this out like this. So the x vector, that's x, y, and z, okay, is equal to p vector plus, again, an s times a u vector plus t times a v vector. Okay, and then they take and break that out. Now remember, x is really equal to x, y, and z, right? And then p is really equal to an x naught, y naught, z naught. That is some initial point. And then u, or not u, stupid. What am I doing? Oh, yeah. U is equal to u1, u2, u3. In other words, the x, y, and z components, and ditto here. And once you understand that concept, the way they do in the book just makes perfect sense. They take this and they just go, you know what, screw that. I'm going to write 3 equations instead. How about that? And they actually refer to this as P1, I believe, in your book, too, which kind of annoys me. Remember, what they really are is X naught, Y naught, and Z naught. They write it this way. And I like this book for the most part. It's just 1 or 2 things it does kind of annoys me. I find it like, could you make it harder? Maybe. Huh. Maybe. Maybe not, though. I don't know. Ta-da! And that, my friends, is what they refer to as the parametric form of it. Okay? Kind of cool, kind of fun, sort of, ish. I did want to show one more thing, and that is when I wrote this earlier, I wrote the normal dot this guy, and it was x minus x naught, if you will, y minus y. I'm going to write like this, I guess, first, and then I'll come back at it. Okay? And that's how we wrote that equation, which was, of course, and what is, and I'll write like this. Maybe. Or something along those lines, right? Where's the x, y, and z components, of course, right? So this is n, obviously. What is this there, though? I feel like this is x minus p. Is it not? And so if one were to dot product this out, one would get n dot x minus n dot p is equal to, of course, is equal to 0, equals 0. And then one could take it a step further. And this is how your book likes to write it. I find this just tedious and off-putting. But if that works for you, you do it, friend. You do it. It's just algebra. That's all it is. Nothing to get concerned about. We all have our favorite ways of doing things, favorite, brand of ketchup, favorite car you like to drive. Honestly, I should be able to get into any car, having driven as long as I have, and be able to drive it. Isn't always true, right? You get in some weird cars, you're like, where's the button? First time I ever drove a Prius, okay? Got in, I'm like, cool. Okay, there's the start button. Oh, okay, so yeah, I get it. This little joystick deal puts me in reverse. Got it. Where's park? Oh, it's this weird P button over here all by itself. What? Took me a while, okay? So some of these are a little tedious, a little weird, a little strange, and no, I would never use them. Probably never in a pinch would I ever use them. So, but I think it's important to understand them and feel good about them so that when you run into one, you know what it's talking about, okay? So I'm going to do a couple more examples here. Just bust through them and see what's happening. See what you think about them, okay? Again, I'm going to start off with 3 points. I find it just a nice, easy way to go about it. Just any points will do because any 3 points, of course, lie in a plane. Remember when I was a kid, this used to really bug me. Oh, that's the equation. That's what a plane looks like. Jay, I'm like, dude, I thought the plane was the tabletop. Yes, but you need 3 points. But no one could ever explain to me when I was a kid why I needed 3 points. Now it makes perfect sense, but back then it did not make sense to me at all, not even a little bit. I had a troubled childhood when it came to mathematics. Okay? I need 2 points. I need 2 vectors. So you do you. It makes no difference. I'm going to go this one and this one just for a good time. Sure, why not? So -3, -5, -11. Truth be told, I probably never do that one in the real world because I don't really dig negatives if I can help them. 1, 10, -1. And it may be such that you're always going to get them. Okay? So I'm going to do this every single way I showed you. Just kind of get to the point, feeling very comfortable about them as I go along. Okay? All right, so number one, I want my normal vector. Okay? To find my normal vector, that is going to equal the cross product of which of course is I times 10, -1, -5, -11, minus, always minus j, 1, -1, -3, -11. It's expansion by minors in case you'd forgotten that back in the day. If you were the guy whose teacher told you how to find a 3 by 3 by the this times that minus this and that, you knock yourself out. It'll work that way. I just don't know how to do it. I never could. -110 minus 5, -115, I think. It's -11 minus 3, -14 plus 14 then. And then that's 5 plus 30 plus 35. Okay. Again, I know I'm right if this comes out to be 0 when I take the dot product with either of these two guys. I'm going to use this one just because I think it's easier. It's going to be 115 negative. That's going to be plus 140. It's going to be minus 35. This is why calculators are a plus in my mind. All right, so second math, vectors, vector ops, cross product. I don't trust myself here, apparently. 1, comma, 10, comma, negative 1. Close the bracket, comma, open the bracket. Negative 3, comma, negative 5, comma, negative 11. Nope. 11 factorial. Yes. What happened? Oh, you hippie. Oh, shut up. Just leave me alone. I hate you too. Ta-da! And it's supposed to be 25. Well, of course it's 25. Which makes this 25. Which makes this equal to 0. Yay, it works. All right, anyway. Again, I think it's pretty cheap insurance to check myself, so I do when I'm doing my normal vectors. So if it's me, I do 115 parentheses. I'm going to do x minus 5 because that's the point that I see, plus 14x minus 6, y minus 6 rather, and then plus 25, and then z minus 18 is equal to 0. Technically, I am done. That is a perfectly legit way of writing that. Now, watch very carefully. If I distribute this, you're going to get this. 575, I believe, plus 14y minus 84 plus 25z minus 900. Oh, 450. Oh, yeah, sure. Duh. Equals 0. Now, watch what I just did. I distributed, yes? This piece right here, this piece right here, and this piece right here are n dot x. Am I right? And this piece, and this piece are n dot p, yes? And so then if I simply take these guys, which are all the constants, and put on the other side, lo and behold, this thing right here is I can't do that math in my head. Negative 450 plus negative 84 plus 575, 41. So equal 41 when I added them up. Positive 41, so I'm going to subtract it over and get negative 41. Okay, lovely. So whether it's in standard form, that is, this guy over here would be on the other side and it equals 0, or in this format here, I'm fine either way how you write that. Okay. Now, if I wanted to write this in vector format, I'd write x is equal to, right? And then I'd have my p plus s times u plus t times v. And my initial point is, well, one of them, so I'll go 5, 6, and 18 again, just because. Plus s times, now my two vectors are 1, 10, and negative 1. And negative 3, negative 5, negative 11. I like this format for one reason and one reason only. It wouldn't make any difference if I swapped these guys around. And it wouldn't make any difference if I had taken and gone the other direction. I did it to be positive. Because I can go negative on the t or positive on the t. I'm going to hit every point in the entire plane, guaranteed, no matter what. Take it to the bank, friend. Take it to the bank. Okay? Now, I feel like I should do... I'm going to solve this guy for z. What do you think? So I'm going to do, it's going to be 115x minus 14y minus 41 over 25 equals z. So again, if one were to plug in a value, try to get a number that's a normal size, so I don't have to like screw around with it. That'd be nice, huh? Yeah. Oh, that's nice. I like that. Okay, good. So I'm going to use 6 for y, and x equals 1. Let's just plug those in. Mostly I just wanted a number that's not ginormous. So 115 minus, and then I said 14 times 6 is 84, and then minus 41 is 10, I think. Negative 10 divided by 25. Negative 10 over 25, which is negative 2/5, so 0.4. Beautiful. Now, I should be able to play the same game down here. X equals 1. And y equals 6. And then, of course, I don't know z, and I will find him momentarily, but of course it's going to require me to find what s and t are, correct? Idiot. True. And so, when I do this, take these top two equations and go to solving them. So I'm going to have s minus 3t equals negative 4, and 10s minus 5t equals 0. That's cute. Times 10. Again, you know, you can do this with a calculator, however you like better. I don't care. Sometimes I like to flex a little bit here, you know. This minus this is 0. This minus this is 25. T equals 40. T equals 40 25ths. Great. So, I don't know, 10s minus 5 times 45ths, I believe, which is 8, isn't it? Well, that's exciting. Isn't that exciting? I think so. Isn't that right? I think so. Yeah. Yeah, that's right. That should be 8 then. Sweet. So then S is equal to 8/10, which is 0.8. Nice. And this is equal to 1.6. So if one were to plug this in, one would get 18 minus 0.8 minus 11 times 1.6, whatever the fink that is. 18 minus 0.8 minus 11 times 1.6. And the answer is negative 0.4. How about that? Yay, we did it, friends. Again, it's a little trickier way of doing it. I don't really care for it, but you know, you do you. 5 plus s minus 3t. This is, of course, the parametric mode. Y equal 6 plus 10s minus 5t. Z equal 8. What is it? 18 minus s minus 11t. Beautiful. That's parametric version of it. Okay? And so that's the game. It's kind of fun. It's almost fun. I don't know if it's fun. It's okay. It's not great. But yeah, kind of fun. Kind of a neat way of going about it. And that's all there is to that. Now, what else did I want to do here? Right. What is the other one I wanted to show you? Well, one moment, please, while I think what I was trying to do. Now, let's talk. How would I do a line in 3 dimensions? How would you do that? Okay. Well, if you think about it, that's really, you're thinking, oh, it's going to be really hard. No, it's not. I'm going from here to here. Okay, if I'm going from here, P to Q, let's say, for instance, Well, obviously I've got a vector. And you're like, well, isn't a vector a line? Well, kind of, but not exactly. A vector is a slope. Okay, that's the slope. This is the change in x, delta y, delta z. And honestly, the easiest way to think about this is where'd you start from? In other words, you started from some x naught, right? And we have to call that a vector, if you will. We're going to add a scalar. And usually the scalar we like to use is time, but not always. Times I like to think of it as a velocity vector, but what is a velocity? It's a rate of change. A change of what? Well, change of x, y, and z. So another way of writing this would be to say x is equal to x naught vector, which we'll call p in a second, but just keep your shirts on. And then times your, I'll call it v for right now, but we can call it whatever we like. So your book refers to it like thus. And I always have to look because it doesn't make sense sometimes the way they write things, but I'll just do it anyway. So yes, theirs is x equals, and we knew this would be p, obviously. And then they do use t here because, again, and most of the time that's what we like. And then they use d instead of v, a velocity vector. But whatevs, man, whatevs. So this equation here would simply be 7, 2, 3 plus t, negative 4, 4, negative 2. Okay, and then if you look at it, well, where am I? Well, I don't know. Where are you? When? Well, when t equals 1, well, I'm here. When t equals 5, I'm, way beyond that point. When t was negative 1, well, I was back down this direction somewhere, yes? And so that's the idea. This line just keeps going on forever. But again, obviously, we can start anywhere, but we'll have the same slope. Now, we might have a multiple of that slope, for instance. We might have negative 8, and negative 4, all right? It could be twice as fast. That's neither here nor there, okay? Because these points live on this line, okay? As do an infinite number of other points that live along that line. Okay, it's a pretty straightforward deal. That's pretty good. Now, there's one last thing is this, and this one here, how far is it from a point to a plane? Okay, so let's say the plane is down here somewhere. That's nice. And this point is up here like so. That's cool. Interesting. Clearly, if one were to stand up here, one would drop a tape measure vertically, thus like so, yes? And we would call this the normal vector. That is our same normal vector that we've been using. Okay, so if we know the equation of the plane, for instance, let's say we know the equation of the plane is ax minus x naught plus b y minus y naught plus c z minus z naught equals 0. If we know a, b, and c, that is, we know the normal vector, we've got this guy. Okay, now let's say there's some point over here somewhere. Okay, this is some other point. This is a point in the plane. Point in the plane. Could be very well be our p from what we've been talking about, some x, y naught, z naught. Now, clearly this is a vector from here to here. Am I right? Clearly that's a vector. You could look at that vector, obviously. Wait, this is obviously also a vector. It's true. Wait a minute. Is there an angle between them? Shut up. There is. Now, wait a minute. Just a minute now, friends. If I were to... Oh, I can't do that. It's going to flip over. Darn it. If one were to draw the sun over yonder... Boing, 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 boing. And this was down this direction. This right here is a projection, yes? And specifically a scalar projection. And so if you're paying attention the other day when I did this one, it's a dot b, but let's worry about that in a second, over the magnitude of a. That's right. Right. Anyway, it's that length right there that matters. And of course, this would be an absolute value because the dot product could, in theory, be negative. So it's the dot product. And so this right here, if you look at it, you're like, oh, that's kind of neat. Well, what is this? Well, this is, one of those guys is the normal vector, yes? That makes sense? One of those is the normal vector. And this is also then the normal vector then. Yes? And so it's pretty easily to do. So we're going to run it through and I'll show you what that means. Now, what this also has a name, this has a name, and this is actually called an orthogonal projection, because it projects it onto the orthogonal vector. Now, interestingly enough, if you've taken any statistics classes, in statistics we talk about doing regression, and we talk about, so we're putting the y's, we're talking about regressing the y's on the x's. We find an equation that fits the line. It doesn't fit perfectly. The errors are the normal, or where the normal is. That is, their errors are off of it a ways. And so it turns out that this, what we're talking about right here, has a relationship to the standard deviation and the variance in statistics. Okay, I just bring that up because it's kind of a neat way of thinking about it, I think, personally. Now, if you look on top, well, what is A? A is just some point. And so I'm going to go back here and define what they called that. I forget what they call that stupid point there. They call that a... oh, for heaven's sakes. Oh, they just call it some random vector v, huh? Okay, well, it's lovely, isn't it now? Let me back that up a little bit. So what I did right there is perfect, and that's great. Of course, I forgot which way your book goes. So this is actually 100% accurate. There's nothing wrong or weird about that at all. We're projecting this vector here onto this guy over here. Okay. Now, then the question then might become, then for some people, is, well, wait just a minute now. Maybe I don't know that vector. Maybe I don't know it. So then I need to know. So if I don't know one of these guys, is there another way to go? And the answer is, well, yeah, there is. Because if you think about it, this right here is, let me draw my picture a little better here. Let's actually just keep going with this here just for a good time, shall we? So this A vector is going to be obviously from here to here, yes? And so it's going to have, if you will, some A1 N1 plus A2 N2 plus A3 N3, right? Okay, over, and when I, this is not wrong here at all. And then of course this can be N1 squared plus N2 squared plus N3 squared, and that's technically 100% accurate. Okay, now the way the book writes it, and it's a nicer formula, if you will. It's on the absolute value of A x naught plus B y naught plus C z naught minus D over this guy. Now be careful. Remember, N is technically A, comma B, comma C. So don't weird it out about that. So what has happened here is that you've taken these guys, but this is if you have the equation in standard format, okay, or the general format. So if I give you I give you AX plus BY plus CZ equals D, right? This is how you go about doing it. Okay, so let's try that just for fun. So let's say I have a plane that is 3x minus y plus z equals 5. Sure, cool. And there is a point 1 comma negative 1 comma 1 that is currently on the plane, obviously on the plane. Cool. And there's a point that's not on the plane, so the point that's not on the plane would be 2, 6, 3. Okay, so again, down here we are. Here's this point here on the plane. Now remember, there's always a normal vector sticking up out of this plane. Okay, we picked the one that happens to go through this guy for the pictures, the purpose of the picture. So we have this vector here. Okay, doesn't matter which way you have that vector going, it's neither here nor there to me. So you have that, and if you look at it, you're gonna have let's see, what are you gonna have? You're gonna have, you know, you can actually draw the picture this way, or you can draw the picture from here, whichever makes you happy. I'm gonna get rid of this guy. This looks like another vector, but it's not. Okay. And so if I look at this picture here, I'm going to go from the plane, this guy down here, 1, -1, 1. I'm going to go up to 2, 6, 3. So that's 1, 5, 7, 2, I think. Is that right? I think so. Good. And we're going to, again, reflect that baby over there. Now I'm going to do it both ways. Okay, so if I was just going to do this thing here, I do A dot B there. Now this, obviously, normal vector is 3, -1, 1. Okay, so if I was to do this with just a projection, it's going to be 1 times 3 plus 7 times -1 plus 2 times 1, absolute value, over the square root of 9 plus 1 plus 1. So I should get 3, 5, -2, so 2 over the square root of 11. That is how long, that is how far it is from here straight down to there. Okay. Now, that's cool, that's great, that's lovely, awesome, whatever. Now, let's see what happens if I did the other way, the way that the book shows. The formula is simply to do this. I want to know how far it is from the point 263 to the plane, which is 3x minus y plus z equals 5. Okay, so the formula simply says do 3 times 2 plus 6 times -1 plus 3 times 1 minus 5 over the square root of 3 plus 1 plus 1, or 9 rather, plus 1 plus 1. So that's going to be obviously 11 on the bottom, and we're going to have 6 minus 6 is 0. Okay. 0. 3 minus 5 is -2. So 2, the absolute value. Ta-da, ta-da. They are the same. Frequently, what you will not have is, in this situation here, well, I already knew. In this situation here, it's 6 to 1/2 dozen the other. I mean, I personally like this setup better because to me it just makes more sense. But this way over here works just as well if you memorize the formula. Okay, this way here in my mind is great because it's just all you're doing is a projection. That's it. That's all, and just the scalar piece of the projection. Over here, this formula gets you to the same place, just maybe not quite as obviously y with the minus d portion of it. Okay, that is section 1.3. I think you should find it to be fairly straightforward.